Hello and welcome to this first video in the A2 syllabus. So we're going to be looking at kinetics. So congratulations, you've survived AS chemistry. If your grades were good and your sanity is still intact, you should probably get yourself a little t-shirt to commemorate that. Because by the end of this it does get tougher, so again, lots of sleepless weekends. The main points what this topic looks at is one, very mathsy calculations, working out the rate constant and its units, and two, the rate determinant step. So we'll jump straight in with the actual numbers. Right, so all rate equations should look something like this. So rate equals, and this is your rate constant, so small k is the rate constant. Why that's introduced is because before it was there, rather than having that, you would just have rate is proportional to the concentration of those raised to the power which they affect it. So rate constant's introduced just as a proportionality to get rid of it. What these represent, it tells you how much the concentration of that species affects the rate of reaction. So it could be that change in the concentration of something has no effect on the rate, whereas for something else could be a small change in the concentration of a species produces a big change in the rate. Where you get these from is actually doing experimental data. So you must actually perform the experiment or be given a table of results. So a balanced molecular equation tells you nothing about the rate. So if I wrote this, that equation there tells me nothing useful about the rate. It just tells me 1 mole of X reacts with 1 mole of Y to give me 1 mole of Z. Useless, really. So what we need is a table of information. You'll have probably done this practical in a PSA, or you'll have done some examples of it. So you'll usually see this in an exam. You'll have a table, unit of rate you should always know. You'll usually be told it, but know it. So moles per decimeter cube per second. These are concentration, so obviously standard unit of concentration, moles per decimeter cubed. So that's why up here square brackets. Square brackets represent concentration. So I'm just going to put some numbers in. Right, so I literally just made these up a couple of minutes ago, that's why nice whole numbers, none of the sort of 0.032 times 10 to the minus 3 stuff which you'll have to deal with, but the methodology will be exactly the same. So what the question will ask you, it will say work out the orders with respect to A, B and C and actually put that into a rate equation. So up here we are going to have some numbers for what the concentration of these are raised to the power of. So how to actually do that? What you need to look for is 2 lines where the concentration of only one reactant changes, because then whatever happens to the rate is purely because of that reactant. So if I compare these 2 lines, lines 1 and 2 for example, C remains constant, B remains constant, A doubles. So now I look at the rate to see what effect that doubling of concentration of A had on the rate. So we can see there that the rate doubled as well. Now, one little way that I like for showing people how to work this out is as follows. So concentration raised to the power of its order is what should happen to the rate. So the concentration went up 2 times. The rate went up 2 times. So it's what do you need to raise 2 to the power of to equal 2? It's 1. So 2 to the power of 1 equals 2. So the order of A is first order. So we'll put that up there. So first order, whatever you do to the concentration is what will happen to the rate. So if I trebled the concentration of A and kept all the others constant, the rate would treble. If I quadrupled A, the rate would quadruple, so forth. So now we'll look at something else. We want to find out the order of B. So if I look at lines 1 and 3 here, you'll notice A remains constant, C remains constant, whereas B trebles. Now look at what happens to the rate. So the rate starts at 5, finishes at 5. So the rate doesn't change, it stays the same, so effectively times 1. So going back to this, what we used before, so what do I need to raise 3 to the power of to equal 1? The answer is 0. Any number to the power of 0 equals 1. So no matter how much I increase that concentration of B, because it is 0 order, nothing will happen to the rate. So I could keep A and C constant, increase the concentration of B by 100 times, and it would have no effect on the rate. So in terms of economy wise, if you're working in industry, it is absolutely pointless having anything more than the bare needed amount of B to get your product, because putting more in will have no effect on the rate. So 0 order. What you will usually see with 0 order ones as well is they are typically even left out of the equation. You can put them in just to feel safe that you know they are 0 order and putting them there. The reason why they are usually left out is obviously concentration to the power of 0. That number there is always going to be 1. So it's going to be K times concentration of A times 1 times concentration of C, whatever that is to the power of. So now to find out C, so I want 2 lines where A and B are the same. So as we can see, lines 1 and 4, they are constant, 0.1, 0.1, so forth there. What happens to the concentration of C? Well, it doubles. Now look at what happens to the rate. So going from 5 to 20, you can see it goes up 4 times. So again, back to this. So the concentration went up 2, rate went up 4. What do you need to raise 2 to the power of to equal 4? 2 to the power of 2, so 2 squared. So if whatever you do to the concentration, square that is what will happen to the rate. So if I treble the concentration of C, 3 squared, the rate would go up 9 times. So it's very useful putting in a fair bit of C because it will increase the rate a lot. So there would be my rate equation. Now in terms of working out K, so this will be the next bit what you'll have to do. You'll have to work out a value for K and the units for K. Now I'm going to rub out some of these lines because you can pick any line to work it out. You use all the numbers from one set line. So it doesn't matter whether you use all of the top line or all of the bottom line, your unit of K should be the same as well as its actual value. So you would need to rearrange this to make K the subject. as such. So again, like I said, I just left out B because that's effectively just going to be a times 1 there, because whatever I put for the concentration to the power of 0 is going to equal 1. So you would put your actual numbers in. So 5 divided by 0.1 times 0.4 squared. Remember that, and your calculator will be a common error. I haven't brought my calculator with me, but I'm sure you can punch that in and work that out for yourself now. So that will give you an actual value for K. The next thing what you'll need to do is work out the unit of K. Way to do that is a little bit of cancelling. So you know the unit of rate. And you know units of concentration, moles per decimeter cubed. Now I've written that longhand just because some people struggle with this. If you are good with maths and the actual powers here in terms of grouping those together, fine, go for it, will be a lot quicker. So you do a little bit of cancelling. So I can cancel 1 out here and 1 out there. So now I would group these together. So effectively I've got 2 moles and 2 dm minus 3s. When you times powers together, you add them. Remember there, you've got a mole plus 1. So plus 1 plus 2. And the minus 3 plus minus 3 minus 6. Now we like to get everything on the top line to go with the S minus 1. So what you do is you flip the actual symbols here. So there, like that. The plus 2 becomes minus 2 and the minus 6 becomes plus 6. S minus 1 is always there, so remember that. There should be a sort of 3 times ratio between these, because obviously mol 1, dm minus 3, 1 to 3 in terms of the number ratio. So the dm value should always be 3 times the mol. Just mental check, because if you've got, say, a 4 and a 14 or something like that, you've obviously ballsed up at some point. So that's working out the rate constant and its unit. In terms of what they would look like graphically, so how the rate is affected by the concentration. So in this case we'll say concentration of B. Now B being 0 order, as I said, no matter what the concentration of B is, it will not affect the rate. So as I increase the concentration on this axis, the rate will not change. It will be a constant, steady rate. So a flat horizontal line there across the page. Now A is first order, so that is linear. So as I said before, if I double the concentration, the rate doubles. If I treble the concentration, rate trebles. So a nice 45-degree angle there coming out, linear, straight line. Now C is second order, so effectively there we're going to have an exponential shaped line, because as the number is low, sort of below 1, then you are going to get a very sort of shallow start. As it gets bigger, sort of 10, 11, so forth, then you will get a much bigger increase in the rate. So you'll have an exponential shaped line like that for C. The other graph what you sometimes have to look at is temperature and how temperature affects K. Now concentration we obviously know should have no effect on K in terms of when we saw that line, no matter which line I pick to actually work out the value, despite having different concentration values, K would remain the same. Because obviously if I increase the concentration of A, then the rate is going to increase. So that kind of has no effect, whereas temperature will affect it. Because you should know from AS chemistry, if you increase the temperature, what will happen to the rate? Obviously it goes up, whereas decrease the temperature, rate will go down. So these will be held constant. If the rate goes up because of an increase in temperature, then the value of K must also go up to balance that out. Vice versa if you decrease the temperature. So the bigger the value of K, the faster your reaction. Smaller K, slower reaction. There is no sort of set value for what is classed as fast and slow. It's all comparative. So one reaction is faster than another reaction. Now the graph would look something like this. You'll notice it's not a straight line because you should remember from GCSE as well as AS, the general rule, every time temperature goes up by about 10 Kelvin, the rate doubles. So obviously your rate is going to start getting much quicker as you go up 10, 10, 10, then it's going to be doubling each time. So likewise, the value of K will also be going up exponentially. Now the final little bit to go into this is the rate determining step. You usually see it shorthanded to just RDS. So an example which I've picked out from a past exam paper. So you were told a few pieces of information. You were told the balanced molecular equation and you were told the rate equation. Now the balanced molecular equation tells you absolutely nothing, remember I'll just reiterate that again, about the rate. So it's going to tell you nothing about the rate determining step. So the rate determining step is which one is actually holding up the reaction. To find out the rate determining step, you need to use the rate equation. So we need to find this is overly simplified by the way in terms of the exam board, so just go with it, especially if you're reading around it more. You need to find the step which just matches the rate equation. So does line 1 match it? We are looking for 1A and 2Bs. Well you'll notice here we've only got 1A and 1B, so no, it's not line 1. So what you would therefore do is drop down to the next step and you would combine the first two steps. So you'll notice the A and the B and the A and the B would cancel each other. So we're left with A plus 2B's goes to AB squared. So 1A, yes. 2B's, yes. So the rate determining step is line 2. And the reason why, very simplistically, because the ratio of these matches the rate equation. And that is it for A2 Kinetics.